All right, let's enjoy center of mass, planar regions. All right, this will correspond to assignment 35. There will only be one homework question because there's multiple parts to this. And so again, just be meticulous and take your time on the homework question. We'll do one example here. So let's just talk in general terms about center of mass and let's try to get an intuitive understanding of it. So Roman numeral 1 in the notes that were uploaded to you, center of mass for a planar region. Let's start easy here. First of all, a lamina is a flat plate of material of uniform density. Now the density, called rho, would depend on the material. So, for example, aluminum has a certain density, bronze has a certain density. So we're not going to specify necessarily the material that's being used because as we'll see as we work through this, you'll see. So we're just going to leave it as rho, and that'll be part of our calculation. But I just want you to understand you could go look up the density of your material if it was made out of copper, bronze, or whatever. So a flat plate of uniform density, aluminum, whatever. So let's talk about a circle. Okay, y'all know what a circle looks like. Of course, here's your circle here. Or let's say a rectangle. There would be another one there. All right. What we're talking about on these copy paper box, pizza. Anyway, we're talking about, when we talk about center of mass, I'm just trying to make this as intuitive as I can. If you continue on with that discussion, the balancing point is what we're looking for. And that's called a centroid in the language that we're going to use. So of all the points on this, where would it balance? If you were to stick a pencil underneath it, where would it balance? And I'm starting with two shapes that would hopefully be intuitive to you. And in calculus, we're going to call that balancing point the centroid, x bar, comma, y bar. Notice it's a point, and that's the ultimate goal. What's the balancing point of that particular object? I picked two that were easy. I hope you would agree that if you were going to look at this circle here and find the point where it would balance, you know, on a pen, right? You would hopefully go, wow, that would be the center, you know, because that's an easy, nice, evenly shaped deal, right? So the center point would be where it would balance. And then, you know, a strategy you might use for a rectangle would be to draw the two diagonals, and then wherever they intersected would be your balancing point. You could put that there and this kind of thing. I've never been an engineer. The closest I've ever come was driving the train at Gage Park. Okay, I didn't even get to drive the train at Gage Park. But anyway, these are important points to engineers because, you know, they want to know where would that object balance? Where's the weight evenly distributed, so to speak? And so those are easy. But the question becomes, what if you had an irregularly shaped object, such as the region bounded by two functions? Where does it balance? So that's what we're working toward. So let's get a picture going of this on example number 1. Find the centroid for the region bounded by the given curves. Well, I would again recommend that we draw a rough picture of this, and I would ask you to do the same thing on this assignment. So if we want to find the region bounded by the two, don't we need to determine where they intersect? And we do that by setting them equal to each other. So this would go back to that, you know, find the points of intersection and things of that nature, and then solve for x. This is just algebra, right? So I don't care how you go about doing it. How about we subtract over the x, we subtract over the 2, we get the equation 0 equals negative x squared plus 3x, 2 goes away. This is just algebra. I would factor out personally negative x, and that leaves x minus 3. I always like to factor the negative out, do whatever you want. And then if you set each of these expressions equal to 0, you would discover that x equals 0, x equals 3. That's where these two graphs cross each other. We'll confirm that in a minute. I just want to get a rough picture. So on this x-axis here, we have 0 and 3 as where they intersect. Let's confirm that. Again, hit pause anytime you want, but this is old stuff. We want to get a picture of the region, and I suppose I could have put that in the notes, but This is old stuff, right? So, anyway, let's confirm 0 plugged in for x is going to give us 2, and 0 in this one is going to give us 2. So the ordered pair is 0, 2. And again, the scale isn't perfect. I'm just trying to get a rough idea of the orientation of these curves. This is all going to come into play. Where do they cross? And we'll continue after that. Let's confirm 3 here. By the way, you'll notice I'm leaving a room here. We're going to test a point in the middle, like we've done before. If we put 3 into this one, 3 plus 2 is 5. And if we put 3 into this one, that would be negative 9 plus 12 plus 2. That'd be 14. That's 5 as well. All right. So 3 on both of them, plots up here at 5. I will be the first to acknowledge to you I'm not taking great care in getting the scale perfect. Just trying to get a rough picture. All right. As we'll see as we move forward, we also at this point need to determine upper, lower. This is all very similar to when we found the area between two curves. So, how about we pick a number between 0 and 3? How about 1? And if you put 1 in this one, 1 plus 2 is 3. And if we put 1 into this one, it's all just arithmetic, right? If we put 1 into this one, let's see, 1 squared with a negative in front of it would be negative 1 plus 4 times 1, which is 4, plus 2, this is just arithmetic, that would be 5. All right, so the hope would be, much like we've seen before, that when we plotted that test point in the middle, we see here that the upper one is 5 and the lower one is 3. So much like we did when we found the area between two curves, we define the region, we find out where they intersect, and then we test that point in the middle. So a rough picture of this would be, and look, that's a line, y equals mx plus b, but you could curvy-worvy it all you want, I don't care, but we'll be quasi-accurate here, that's a line. And then wouldn't this be a parabola that opens downward? But the main point is get a picture of upper and lower. And to correspond to the labels we're going to see later, let's call that upper curve f of x. You're going to see these references later. And let's call the lower one g of x, much like we've done before. Okay? So, we've been there, done that. Here's what I'm asking you to think about. Suppose you were to cut out this object, and it would create, a flat plate of material, and it's made of aluminum or something, and you want to know what point would be the balancing point. Where would that thing balance? Where would the area be evenly distributed, so to speak? So, well, all right, there's a ton of theory behind this, and so, I struggle with this as to how deep to go into the theory of it. And I'm a realist. I think, given our circumstances, we need to just talk through what's basically the procedure for finding this. And so if you go on to the slide that says center of mass, planar region, we're about to go through 4 things here to get that balancing point. All right, what point would be the balancing point for that somewhat irregularly shaped object? So, the first step is to find our mass, and that's going to be a lowercase m, and again, you have these notes, they've been uploaded to you. So the mass, that'll be the first thing we're going to do here. And I'm nervous about running out of space here, so I hope this fits. But the mass, lowercase m, would be rho. I want to remind you, rho is the density of the material. Now, we're not going to tell you what this is made out of. We'll talk about this later. So you just say, okay, I could go look up if this was made out of aluminum, I'd look up the density of aluminum and put that in for rho. Same, if it was copper, I'd look up the density. You could go Google that, right? So, and then we're going to integrate from a to b, which in this case would be from 0 to 3, those points of intersection, the interval over which this is bounded. And then this is the upper function, f of x minus the lower function g of x. And again, with respect to x. It's always important when you set up an integral that you put with respect to what variable. And that becomes even more important when you get to Calc 2. All right, so moving on from there, rho, integral from 0 to 2. Anybody else hearing row your boat in your head? You probably weren't, but you're welcome now. All right, if you distribute the negative and combine some like terms, it looks like this thing would simplify to negative x squared plus 3x, and the 2's would subtract out, and that would be the setup for that. Okay, now, the deeper you get into math, the deeper you get into calculus, this is the point where you would say, total snob here, but evaluating that integral is something we've been doing for quite some time. The antiderivative of this would be negative x cubed over 3 plus 3x squared over 2. It's just terms, powers. You would go back and do that integrate, evaluate, celebrate, graduate, compensate. The point is, all that right there would create a number, wouldn't it? That integral, that definite integral, f of b minus f of a and all that. So, I just got to tell you that's old stuff. I did the work ahead of time. You will also see this on an answer slide that has been uploaded, but that integral in this case comes out to be 4.5. And so the mass of this particular object would be 4.5 times whatever the density of the material was. Whether it's aluminum, copper, you get the idea. So there you go. That's just a mechanical thing, and that would be the setup for finding our mass. Boom. That's step 1. Step 2, step B, I guess in your notes, find what's called the moment about the x-axis. And again, this is all real smart math people figured all these things out for us. I got to make some room for this because I can tell I'm going to run out of space if I'm not careful. So again, hit pause if you need to. The setup for mass was to subtract the 2, upper minus lower, boom. Integrate, evaluate, get your number, times rho. All right, mass. Wish me luck. I hope there's room here. All right. The moment about the x-axis. All right. Moment x-axis. All right. Again, this is a cookbook kind of thing. I guess I'll put the setup up here and hope it fits. Board space is difficult here, but we're making it work. All right, so the moment about the x-axis, you can see here, smart math people figured all these things out. And again, given the circumstances, let's just go through how you do it. In fact, this is a beginning course in calc, so I don't know, call me lazy if you want. I'm not talking about where these things come from. 1/2 rho, integral from a to b, 0 to 3, okay? F of x plus g of x. I'm going to simplify this and then transfer it down here like I've been doing. Well, that would be the upper curve plus the lower curve. Okay, so that's this part of it, f of x plus g of x, add the two functions basically. And then look, if you're paying attention here, and I'm guilty of not always paying attention, but then you multiply that quantity with f of x minus g of x, which I want to remind you would be the expression we got when we did mass. So why reinvent the wheel? The f of x minus the g of x would be the negative x squared plus 3x that we did when we did mass. So that would be the setup for finding the moment about the x-axis. And transferring that down and cleaning it up a little bit. And again, the symbol for this is m subscript x, moment about the x-axis. And I keep testing these markers here. I hope these work. 1/2 rho, density of the material. That's a Greek letter rho, not p. All right. Integral from 0 to 3. All right, look, you clean this up in here. So that first bracket would be what? Negative x squared plus 5x plus 4, basically combining like terms, and then times the negative x squared plus 3x. And once again, this is all with respect to x. Now, honestly, cleaning this one up and crunching it out, a little bit more complicated. It is just algebra. One would need to distribute all these terms with each other and simplify and combine like terms. And ready, everybody? 1, 2, 3. That's just algebra. It's brute force. That's why I'm only going to give you one of these to work. All right? But you would distribute that all out. It would end up being terms with powers. You could then apply the power rule to each term to get that antiderivative, and then you would evaluate it. So we've talked about that before. Now, another thing that's easy to miss on this would be that after you evaluate that integral, as I just described, I'm going off screen to look for a better marker, all right? Keep shaking them down, hopefully they work here. Remember on this one, that after you get that number from that integral, it needs to be multiplied by a half. Okay, so make sure you're careful with that. So the value of that integral, brute force, go do it. Okay, you can do it, it's algebra, times a half. And it turns out, I know it's lazy, but look, we got to push you out of the nest at some point. I'm trying to get you used to that kind of thing where we go, hey, you're big calculus people now. So that integral apparently was double this times a half, 19.8, and then rho. So that's the moment about the x-axis after you go do all those mechanical things. Woohoo! Alrighty, so hit pause, digest that, go off and practice. Distribute this, do the power rule to each term, f of b minus f of a, all that. You know the drill. Okay, so I'm going to erase this setup here because, again, board space is at a premium, and this would be our setup for the moment about the x-axis. We're getting closer. I think we're going to fit here. I hope so. All right. Next idea. Moment about y-axis. And again, I think this is staying in the frame. I sure hope so. This is all cookbook. I know I keep saying it. Smart math people figured these things out for us. If you want to get deeper into it, you can read the book. And where'd this formula come from? The moment about the y-axis is m subscript y. I'm just showing you the mechanics of how to get this stuff, all right? Rho, that would be the density of the material, aluminum, whatever. We're cutting this out. You know, it could be made out of anything. And then this is the integral. Oh boy, I'm getting close to the edge. From 0 to 3. Okay, now look, this is very similar to our mass expression. We have x times the difference between the two functions. So that would be x times, and again, as mentioned earlier, the f of x minus g of x was what we did. Why reinvent the wheel? That was the expression for mass back here, the integral in there, the integrand. So negative x squared plus 3x. dx. Sorry, I had to, could have written smaller earlier. I don't know, it's hard to rehearse this. But I hope you see that. Now, just like this was distributing, wouldn't that be distribute the x into the parentheses? That wouldn't be that bad. And so you'd clean up that integrand, you'd have a couple terms there, and then you would find the antiderivatives of each of those two terms, and then put 3 in, minus, put 0 in, f of b minus f of a, all that stuff we talked about earlier when we talked about how to evaluate a definite integral. I've been doing this for quite a while. Former students have told me, yeah, that's fair. And so, just to keep things moving, the moment about the y-axis, that integral ends up being 6.75, and then again you multiply that by the density of your material. And you're going, well, are you going to tell us what the material is? No. We don't need to know it. And here's why. The final step, which I believe we'll be able to do up here, okay, what is that actual balancing point known as the centroid? It's an ordered pair, okay? And again, these numbers down here are going to be used to find this centroid. It is given x bar, y bar, the balancing point, the centroid, by the following expression. The moment about the y-axis divided by mass. So the x-coordinate would be the moment about the y-axis, 6.75 rho, divided by the mass, which was 4.5 rho. We'll simplify that in a moment. That will be the x-coordinate of our balancing point, x bar. The y-coordinate of our balancing point, and I know it seems counterintuitive that this involves x, and that involves y. It's easy to get them backwards. But that's the moment about the x-axis, which turned out to be 19.8 rho, divided by mass, which is 4.5 rho. So now you see why we needed these different things. And you know, the interesting thing about this is why I keep mentioning this, but when we go to simplify this, you will notice that in both cases, the rho cancels in both fractions, because guess what? The balancing point here really doesn't matter whether it's made out of aluminum, copper, whatever. It turns out that the balancing point is going to be the same regardless of the material. So the density of the material turns out to be immaterial, right? So 6.75 divided by 4.5. Did the math ahead of time. That turns out to be 1.5. And the other one turns out to be 4.4. Now the 1.5 is halfway between here. That was just kind of coincidence. It wouldn't have to be that way. Don't just think you find the midpoint of your interval. That happened here. Maybe I should change the question so that does not occur. If that would have been a curve, then that wouldn't have happened. But the idea would be the ordered pair of 1.5, 4.4 would be, if we were to cut that out, pull it off the board, that would be the point where it would balance. So, again, you have one of these to enjoy, and be very careful. I will be the first to acknowledge to you that I was pretty lazy when it came to this, but I hope you understand my dilemma here. I was lucky to fit this on the board as is, but calculating each of those integrals is stuff we've talked about before. And yes, it will be some brute force, but I will tell you that you won't need to do substitution or anything like that. You'll have terms with powers, which is the most basic type of integral there is. You'll have to do some simplification using just algebra on some of them, but it'll follow a pretty similar format as this one. So, yay! That will be indeed assignment number 35. So I wish you the best of luck, and not sure what else to say. You hang up first. No, you hang up first. No, you. Okay, okay, sorry. Whew. Mr. Snickerdoodle really misses you guys. I wish we were here enjoying this together. Take care of yourselves, take care of your families. Let's move on.